A starship leaves Earth, spends 100 years in the dark, and finally drops into the gravity well of a new star. But that arrival is where things get dangerous. No real-time help from home, brutal orbital mechanics, unknown atmospheres, and a crew that's biologically and culturally a century out of sync with Earth. In this video, we break down what actually happens the moment a 100-year starship reaches its destination, and why that changes humanity forever. But before we continue, please subscribe to the channel if you enjoy the video. Let's continue. You covered the distance by cruising at around 1/10 the speed of light, about 30,000 kilometers per second, around 19,000 miles per second. For most of that journey, space outside the hull was almost empty and almost perfectly dark. The background glow of the galaxy and a thin drizzle of particles. That was it. As you move into the star's territory, that changes fast. Photon levels rise. The star is still a point, but it's now much brighter than the background. And instruments start seeing a clear gradient in light and particle flow. The local interstellar medium, a very thin gas, gives way to the star's wind, a stream of charged particles blowing outward at hundreds of kilometers per second, a few hundred miles per second. Your detectors see the particle counts ramp up, and the radiation spectrum shifts. You've stepped from between stars into the bubble controlled by this one star. This is the real start of arrival. Your sensors flip from low signal, deep space modes to high rate, near star modes. Shielding is tested harder. Your navigation filters now include pressure from that wind, not just gravity. And all of this is happening after a full century of flight, which leads to the next hard question. Whose 100 years was it exactly? Yours or Earth's? At the speeds we talk about for a realistic interstellar mission, relativity matters, but it doesn't turn you into a sci-fi time tourist. At around 1/10 light speed, the relativistic correction to time, the gamma factor, is only a bit above 1. That means if clocks on Earth record 100 years, clocks on your ship record roughly 99.5. You gain maybe 6 months over a century. From a physics point of view, that's a small correction. But if your engineering allows something like half the speed of light, 150,000 kilometers per second, about 93,000 miles per second, the effect becomes more serious. Now that gamma factor is around 1.15. Earth sees 100 years pass, while people on the ship feel only about 87. 13 extra years pass on Earth compared to your lived time. That still doesn't let you go back and meet your great-grandparents. But socially, it's a big deal. A teenager at launch, if they somehow live through the whole flight, arrives as a very old person. Their family back on Earth, if any line still exists, is several generations beyond them. Companies, even entire nations that sent you out, may not exist anymore. The date in your ship's internal records and the date on Earth diverge, and they will never match again. Now add another delay on top, the communication lag. You've finally reached the target star. Can Earth still guide you, or are you on your own? Proxima Centauri is about 4.24 light years away. Light speed is the absolute upper limit. That means any radio or laser signal you send takes 4.24 years to get to Earth. That's roughly 1.3 billion seconds for a single one-way message. You say, "We have arrived, we are starting orbital insertion," and nobody on Earth reads that for more than 4 years. Their reply, if they send one immediately, takes another 4 years to reach you. So there is no real-time mission control. There is no turn left now from Earth. By the time any suggestion or correction arrives, your situation has changed completely. In practice, your messages turn into status reports and science dumps, not requests for instructions. For Earth, every signal is news. From almost half a decade in your past. For you, every reply is from a world that is years out of date. That pushes the mission into a very different mode. Your autonomous systems, and your onboard crew if you have humans, are the only actual decision makers. Earth is more like a distant archive and a funding source from the past than an active controller. And all of this assumes that the Starship even hit the right target. After 100 years, what guarantees that you didn't miss by a huge distance? Stars move. They orbit the center of the galaxy, just like the sun does. On the sky, that motion shows up as proper motion, small shifts in position over time. Proxima's apparent motion is about 3.8 arcseconds per year. That is a tiny angle, But give it a century, and the total shift is hundreds of arcseconds, more than a tenth of a degree. Over several light years, that corresponds to a change of billions of kilometers, billions of miles between the coordinates at launch and the coordinates at arrival. If your navigation system just locked on to the launch day coordinates, fired the engines and never updated, the ship would arrive in roughly the right direction, but not close to the star. At a few tenths of light speed, you would pass the system at a huge miss distance, far too large to make a serious course correction with the fuel you have left. So the ship needs its own high-precision navigation. It flies with star trackers that compare the positions of background stars to an internal catalogue. It might use pulsars, those rapidly spinning neutron stars that emit very regular flashes, as timing beacons, measuring their arrival times to estimate its own location. It can point narrow telescopes at known quasars, extremely distant and stable sources, to build a fixed reference frame. Over the whole century, the guidance software keeps updating the target's predicted position and applies small engine burns, tiny corrections, to keep you on a path that actually intersects the star's sphere of influence. Hundreds of micro-adjustments over decades are what let you slip into the system, rather than streak past. But even if you succeed at that, there's one more layer of uncertainty. Is the star you find at the end of the trip the same kind of star you designed for? Stars are not perfectly stable lamps. Our sun has an 11-year cycle where magnetic activity rises and falls. When activity is high, you see more sunspots, more flares, more high-energy particles. Other sun-like stars have similar cycles, often between about 5 and 20 years. Red dwarfs, like Proxima, can be much more active, with frequent, powerful flares that blast out intense ultraviolet and X-ray radiation. In one century, that star can go through many such cycles. The average flare rate can drift. The long-term magnetic field can rearrange. The structure and density of the stellar wind can change. From a human point of view, 100 years is a long, complicated time. From the star's point of view, it's only a small slice of its life, but that slice can still be very different from the one your mission planners studied. So you may arrive at a star that is brighter or dimmer in certain wavelengths, has a stronger or weaker wind, and sends out more or fewer giant flares than expected. That changes the radiation environment for any planets. It changes how thick your shielding needs to be. It changes how close you dare bring the ship for braking maneuvers, and how safe any early probes and landers will be. You started with models built from distant telescopes and simulations. You end with reality, and reality might not match the plan, which forces a tougher question. If the star itself is more hostile and you're still coming in at a big fraction of light speed, how do you slow this 1,000-ton machine down without turning it into debris? You're carrying the energy of hundreds of thousands of nuclear bombs, and you need to get rid of it without dying. How do you do that? Take a solid number. Your Starship masses around 1,000 tons, roughly 1 million kilograms, similar to a small skyscraper. You're moving at 0.2 times the speed of light, about 60,000 kilometers per second, around 37,000 miles per second. If you plug those numbers into the basic kinetic energy formula, you end up with something like 10 to the power of 21 joules. That's about 400,000 times the energy of the biggest nuclear bomb ever tested on Earth. That is what you have to turn off just to stop in this new star system. You can't just slam the engines into reverse and hope for the best. If you try to stop too fast, the deceleration forces will crush the ship. At 1 g Earth gravity, you'd need on the order of a couple of months of continuous braking to bleed off that speed. At 1/100th of that, 0.01 g, you're looking at many years. All that time, that enormous energy has to flow somewhere, into exhaust, into heat, into radiation, without cooking the crew or melting the machinery. So the first blunt question is, what engine are you actually using to dump that energy? For most realistic designs, the answer is some form of fusion rocket. You fuse light nuclei like deuterium and tritium, release huge amounts of energy, and throw the fusion products out the back at very high speed. Numbers people like to quote for an advanced fusion drive are exhaust speeds around 10,000 kilometers per second, roughly 6,000 miles per second. That is still only a few percent of light speed, but it is far better than chemical rockets. With exhaust that fast, you can, in theory, change your ship's speed by a large fraction of light speed. But there's a catch. To cut your velocity in half, you generally have to throw away a chunk of mass similar to the mass of your ship, maybe more, as hot exhaust. That means if your dry ship is 1,000 tons, you need thousands of tons of fusion fuel and engine structure just to brake, on top of whatever you use to accelerate back home. And right now on Earth, fusion is barely at the stage of breaking even in large experiments. Tokamaks use huge magnetic fields to confine plasma. Laser inertial setups blast tiny pellets. They produce fusion reactions, but they do it in controlled lab conditions, not in a compact high-thrust engine you can throttle up and down for months in deep space. So a working fusion drive for a Starship is not just a bigger version of what we have. It is at least a century of research and engineering on top of today's technology, but still based on the same measured reaction physics. Even if humanity solves that, and you have a fusion drive that can run for months at a time, you still have a serious downside. Carrying that fuel for both acceleration and braking makes your ship heavy, expensive, and complex. So the next move is obvious. Is there any way to use the star itself to slow down and carry less fuel? One leading idea is the magnetic sail, or magsail. Instead of relying only on your rocket, you deploy a huge loop of superconducting wire, tens or maybe hundreds of kilometers wide. You run current through it, and it blows up a magnetic field bubble around your ship, much larger than the physical structure. When the charged particles in the star's wind hit that magnetic field, they get deflected. That deflection transfers momentum from your ship into the plasma. You don't actually touch any gas with a physical sail, you touch it with your magnetic field. The deceleration is gentle, maybe tiny fractions of a g, but at 0.1 to 0.2 times light speed, you sweep through millions of kilometers every hour. A small braking force applied over months or years out in the star's outer system can subtract a big chunk of your speed before you ever reach the inner planets. This also combines nicely with a light sail, if you used one for acceleration. Far from the star, the light pressure is weak but still usable. Closer in, the particle wind picks up and the magsail does more work. But this solution has its own problems. You need superconductors that can hold huge currents for decades without failing. The sail has to survive micrometeoroid hits and variations in the stellar wind. And if the star is more active than expected, sudden storms of particles and magnetic changes can hammer your sail harder than your design allowed. So you can try to ride the star's wind to slow down, but maybe that's still not enough. In that case, another option appears, and it is much more violent, using a gas giant's atmosphere itself as your brake. This is air capture, scaled up to terrifying levels. Space agencies have already done soft versions of this in our solar system. At Mars, for example, orbiters dipped into the upper atmosphere again and again, skimming through thin air at a few kilometers per second, a few miles per second, to slowly reduce speed and circularize their orbits. The key was using the atmosphere as a free brake, instead of burning huge amounts of fuel. Now scale that to an interstellar ship. You arrive in the target system still moving at tens of kilometers per second relative to a massive gas giant, maybe 50 kilometers per second, about 31 miles per second, or more. You aim the ship so it just grazes the upper layers of the gas giant's atmosphere. The friction and compression of the gas around your heat shield convert a large slice of your kinetic energy straight into heat and light. The shock layer in front of you glows white-hot plasma. A miscalculation of a few tenths of a degree in the entry angle is the difference between skipping out of the atmosphere and flying off into space forever, or going too deep and burning and crushing the ship. The heating rate is extreme, far above what current Mars missions see. Your shield has to survive temperatures and thermal loads that would shred normal materials. The structure has to handle deceleration of several G, maybe more, spread over minutes without snapping. Every parameter, density, lift, drag, entry angle, has to be pre-computed, modelled, and tested by simulation long before you arrive. There is no time to try again. You only get one pass. Even with fusion drives, magsails, and aerocapture on the table, there is a final, very simple outcome that mission planners have to accept. What if you don't stop at all? In that case, arrival is really just a high-speed flyby. The ship stays at a big fraction of light speed the entire time. It dives through the target system once, gathers as much data as possible, and then keeps going into interstellar space on a new course. This is closer to the way we explored the outer solar system early on. Voyager 1 and 2 didn't stop at Jupiter or Saturn. New Horizons didn't stop at Pluto. They flew past once, at high speed, took their measurements and left. At 0.2 times light speed, your crossing time through the inner region of a star system is short. You might spend only hours near the distance where Earth orbits the Sun, maybe a day or two in the whole inner system. That means your sensors have to be pointed, focused, and ready. You have to plan the exact trajectory years in advance so that at the right moments cameras, spectrometers, and particle detectors are aimed at the planets and the star. You still get science. You can still map orbits, measure atmospheres, detect magnetic fields, and search for signs of life. But you never enter orbit. You never build local infrastructure. The ship itself becomes a one-time probe, a ghost slashing past the star and vanishing back into the dark, carrying its data outwards and beaming it home over years. And all of this, the fusion burns, the magnetic sails, the gas giant dives, or the one-way flyby, happens while you are moving from the emptiness between stars into the crowded, messy bubble of gas and fields around this new sun. So the next question is, when you finally cross the invisible border between interstellar space and the star's own bubble, what changes for your ship? What actually happens when you cross the invisible border between interstellar space and a star's personal bubble? For most of your trip, you're in the local interstellar medium. That's not truly empty. It's a very thin gas, maybe 0.1 to 1 atom in every cubic centimetre. That's better vacuum than we can make in most lab chambers on Earth. Your ship moves through this stuff for decades at high speed, and your instruments see a fairly steady pattern. Low-density gas, background magnetic fields from the galaxy, and a constant rain of high-energy cosmic rays. As you approach the new star, those readings start to drift. The density and direction of the plasma around you change. The magnetic field strength climbs, and its direction swivels. At some distance, maybe 100 astronomical units out, maybe more or less depending on the star, the balance tips. The star's own wind becomes stronger than the surrounding interstellar gas. That region is the star's heliosphere. Or, more generally, its astrosphere. For comparison, our sun's boundary, the heliopause, is around 120 astronomical units out, more than 100 times the Earth-Sun distance, over 18 billion kilometres, about 11 billion miles. Voyager 1 crossed it and saw a sharp drop in solar wind speed and a change in particle populations. Your ship is now doing the same kind of crossing, but at much higher speed and with far better instruments. The transition is not a hard metal wall, but your instruments see it like one. Particle detectors, which count ions and electrons, show a sudden change. Magnetic field sensors see the field direction flip from the orientation of the galactic field to the twisted field dragged out by the star. Plasma wave instruments pick up different kinds of turbulence. By comparing how much pressure comes from the star's wind and how much from the external gas, you can say how strong this star's bubble is compared to our sun's. That boundary is a physics goldmine. Back home, we only had one example, our heliosphere. Now you have a second full-scale test. You can measure how fast the stellar wind slows down as it piles into the interstellar medium, how sharp or smooth the shock is, and how much energy goes into heating, waves, and magnetic structures. All of that feeds back into models of how stars carve out cavities in the galaxy, and how those cavities protect planets. This leads straight to a key question for the humans on board, or for any future crews. Does crossing into this bubble make space more dangerous or less? Out in deep interstellar space, your biggest radiation problem is high-energy cosmic rays. These are particles, mostly protons and heavier nuclei, moving at relativistic speeds, with energies in the giga-electron-volt range and beyond. They slam into your hull, produce showers of secondary particles, and slowly damage electronics and biological tissue. Even with shielding, over 100 years, that dose adds up. Inside a star's heliosphere, many of those particles are blocked or slowed by the star's magnetic field and wind. The field lines act like a filter, deflecting the lower energy cosmic rays and reducing the overall flux. That doesn't mean space is suddenly safe. You still have solar energetic particles from flares and coronal mass ejections, but the very highest energy cosmic rays that punch deepest into shielding drop in number. On your ship, Dosimeters and radiation monitors see this directly. Over a period of days or weeks as you move inside the astrosphere, they record a trend, a reduction in background cosmic ray counts, and a shift in the energy spectrum of what still gets through. For a crew, this is good news. Long-term cancer risk and electronics damage both get slightly better inside a well-formed stellar bubble than in raw interstellar space. But that same protective bubble is built on magnetic fields, and those fields are not simple. So the next task is clear. How do you actually map the magnetic skeleton of this new system? Stars rotate and carry magnetic fields with them. The solar wind drags the sun's field outwards, and because the sun spins roughly once every 25 days, that field gets wound into a spiral pattern. As your ship penetrates deeper into the new star's heliosphere, its magnetometers trace out the equivalent pattern. They see how strong the field is, what direction it points, and how fast it changes with distance and time. Over months and years, you can reconstruct the star's rotation period from subtle changes in field direction. You can detect large-scale flips when the star's global field reverses polarity over its activity cycle, similar to the sun's 11-year flip. You can see how far the magnetic influence extends along the star's equatorial plane compared to its poles. From Earth, most of this is guesswork. We infer magnetic cycles from changes in brightness and in certain spectral lines. From your position inside the bubble, you're doing direct sampling. You make an actual map, a three-dimensional model of how the field threads through space, where it is strong, where it is weak, and how it couples to any planets and moons. This isn't just interesting physics, it's also a warning system, because those fields and the star's wind create space weather that any future colony has to survive. So the next thing you care about is simple. How violent is this system? Really, on Earth, we have a magnetosphere and a thick atmosphere that soak up most of the damage from solar storms. When a coronal mass ejection hits, our magnetic field shunts much of the energy around the planet. We still get auroras, satellite issues, and occasional power grid problems, but the surface is mostly safe. In this new system, you do not assume that. From your vantage point, you watch how often the star throws off big eruptions. You measure the density, speed, and composition of those ejected clouds as they pass your instruments. You look at how far from the star they are still dangerous. At one astronomical unit, about 150 million kilometers, or 93 million miles, you ask, how intense are the particle blasts? How often do they hit? You also measure the baseline wind speed and density at various distances. You monitor how quickly conditions change during a storm, how strongly the magnetic field spikes, and how the local plasma responds. If there are planets in or near the habitable zone, you can simulate what those storms would do to their atmospheres and magnetospheres. From those numbers, you can say very practical things. A surface settlement on an unmagnetized planet here may need to be built underground or under thick rock to cut radiation spikes. A free-flying space habitat might need heavy storm shelters and the ability to rotate its orientation relative to the incoming blast. Communication systems will need redundancy to handle long outages during extreme events. The heliosphere, then, is not just a nice boundary in a diagram. It is the environmental control system for the entire star system. By measuring its size, its structure, its shielding power, and its storms, you are deciding where humans can safely live, what kind of hardware will survive, and how often everything will be hit by space weather that can kill. And once you understand the bubble you've just entered, you hit the next step. Now that you're inside, how do you turn this entire star system into a lab and scan every planet, moon, and ring before you even think about landing? You've stared at this system as a set of numbers and blurry pixels for decades. Now you're finally close. So how fast can you turn those pixels into actual planets? From Earth, most exoplanets are just tiny dips in starlight, or at best a single pixel buried in the glare of their star. Out here inside the system, everything changes. Your telescopes are now millions of kilometers away from the targets, not trillions. A 10-meter mirror at a distance of 1 million kilometers can, with good optics, pick out surface details on the scale of tens of kilometers, tens of miles. That's sharper than any exoplanet image we can get from Earth, by an absurd margin. So the first phase is simple and brutal. Point every instrument you have at everything that moves. You start with wide field surveys, scanning for planets, moons, rings, asteroid belts. You lock onto each candidate and run rapid imaging sequences. Within hours, the planet B that used to be one data point on a light curve turns into an actual disk with bright and dark regions. You see cloud bands, ice caps, maybe even ring systems and large storms. Moons show up as moving points that orbit those disks. Resolution is now a geometry problem, not a distant hope. The closer you fly, the sharper things get. At a few million kilometers, your big telescope is seeing details comparable to what Earth orbiters see on Mars. You can schedule repeated passes, building up maps as the planet rotates. Day by day, the system stops being a set of catalogue entries and becomes a set of places with specific shapes and layouts. Once you can see surfaces, the next obvious question hits. What is all this stuff actually made of, in the air and on the ground? That's where spectra stop being a vague hint and start becoming hard numbers. From Earth, we mostly study exoplanet atmospheres by watching a planet pass in front of its star, letting starlight filter through the atmosphere. The tiny changes in colour tell us what gases might be there, but the signals are weak and noisy. Here, in system, you don't have to wait for perfect transits. You can look at starlight reflected off the day side of a planet. You can look at the planet's own thermal glow from the night side, especially in the infrared. You can even aim at the thin ring of atmosphere at the limb during local sunrise or sunset, and read it like a barcode. With high-resolution spectrometers, you start pulling out exact mixing ratios. How much methane in parts per million? How much carbon dioxide? How much water vapour? You can estimate oxygen partial pressure and see whether it's at trace levels like Mars or 20% like Earth, or something completely different. Aerosols in the air, like dust or haze or sulfuric droplets, show up as broad features that dim or scatter certain wavelengths. From that, you get aerosol optical depth, a measure of how murky the sky really is. You do this not just for one world, but for every major planet and selected moons. You quickly see which ones have thick atmospheres, which ones are thin and airless, which ones are dominated by hydrogen and helium, which ones are loaded with heavier molecules. In a short time, you move from maybe this has an atmosphere to here is the composition, with uncertainties of only a few percent. Once you understand the air, the next question goes deeper. Literally, what is happening under the surface? Your ship and any orbiters you deploy are constantly being tugged by gravity, not just by the star, but by every planet, moon, and large asteroid they pass. Those tugs are tiny, but your navigation systems track velocity and position to absurd precision. By analysing the way your path bends and wobbles as you fly past a planet, you can map out variations in the planet's gravity field. This is the same basic idea used by missions like Grail at the Moon and Grace at Earth. If a region under the surface is denser, maybe because of a metal-rich core or a big slab of rock, the gravity there is slightly stronger. If there's a buried ocean or a less dense mantle, the gravity is slightly weaker. By flying a network of passes at different altitudes and latitudes, then solving the math, you build a gravity map. From the overall mass and radius, you get the planet's average density. For Earth, that's about 5,500 kilograms per cubic meter. If your target planet has similar or higher average density, it's probably rocky and iron-rich. If it's much lower, it may have a large water layer or be more like a mini Neptune. Local gravity anomalies then add detail, suggesting thick crust here, thin crust there, possible mantle plumes, or hidden basins that could once have held oceans. With gravity, you start to see the skeleton of each world. But to interpret that skeleton, you lean on something you already know very well, the solar system you came from. So the next step is obvious. Which of these worlds look like the ones we've already dissected, and which ones do not fit anything we've seen? Back home, missions have drilled into the moon, roved on Mars, dived into Jupiter's gravity field, skimmed Titan's atmosphere. We have radar maps, magnetometer data, neutron counts, seismic readings. We know typical crust thicknesses, like Mars at around 50 kilometers on average. We know water contents like Europa with tens of kilometers of ice over a liquid ocean. We know what a strong, intrinsic magnetic field looks like at close range, from Earth and Mercury, and what a mostly dead field looks like, from Mars. Your instruments are built by people who lived through that learning, So when your magnetometers see a certain strength and pattern, you can say, this world has an active dynamo closer to Earth than Mars. When your neutron detectors pick up signatures of hydrogen just under the surface of a moon, you can say, there is likely water ice here, in this depth range. When your radar sounders find a sharp boundary under an ice shell, you can say, that is probably a liquid layer. As the data flows in, every target in this new system gets slotted into a mental library. This one is Mars-like, but wetter. That one is a scaled-up Europa with thicker ice. Another might be a strange mix, Earth density, but no sign of plate tectonics. You are not speaking poetically, you are matching measured kilometers and densities and field strengths against the massive database built in the home system. Even with all this, you are still only at the start. So the next issue is about time. How much can you really learn in those first frantic days and weeks, and how much will stay uncertain for decades? The early survey is fast and rough, but extremely valuable. Within days, you pin down the orbital periods of every big planet and many moons, accurate to minutes. Within weeks, you refine masses to fractions of a percent. Temperature maps from infrared scans give you average dayside and nightside temperatures to within a few Kelvin. You spot seasonal patterns if you happen to arrive at a time when the star-planet geometry is changing. You quickly build a basic climate picture. Which worlds have thick greenhouse blankets? Which ones are frozen? Which ones show signs of active weather? You also log all the obvious red flag signals: strong methane with no obvious geological source, oxygen out of chemical balance, strange surface colours that might be pigments. But the deep questions, climate history, geological timescales, and especially biology, cannot be answered that fast. You can see river-like channels, but you need models and maybe landers to say how old they are. You can see layered deposits, but you need long-term monitoring to say how often dust storms or ice ages reshape them. You can see interesting atmospheric chemistry, but you need years of data and careful lab work, back on Earth and in your new system, to separate life signals from exotic but non-living chemistry. So the first system-wide scan is like an emergency room triage. You decide which worlds are boring rocks, which are dangerous gas giants, which are icy resource banks, and which are truly special. You tag targets for landers, for orbiters, for eventual human bases. You also generate a to-do list that will take decades to finish. And standing out on that list, highlighted from day one, is the world that pulled you here in the first place, the exoplanet that looked just right from 4 light years away. Now that you're close, when you finally turn everything on that one planet, does it actually match the picture that sent humanity across interstellar space? Or does it break every expectation? You crossed interstellar space for one main reason. This one planet looked worth the risk. Now you're close enough to see it as a disk, not a data point. So the big question is simple. Does it match the promise that sent you here? Back on Earth, this world started as a pattern in a light curve, tiny dips in the star's brightness as the planet crossed in front. From those dips, you got its radius, about 1.3 times Earth's. From the tiny wobble of the star itself, you got its mass, around 2.5 times Earth's. Put those together, mass divided by volume, and you got a bulk density of roughly 5,600 kilograms per cubic meter, close to Earth's. That screamed rocky super-Earth, not a puffy mini Neptune. Now you're here, and you can actually check. You track the planet's pull on your ship, you track small probes in orbit, you time their passes, you watch how their paths bend when they fly over different regions. That gives you a precise mass. You measure its actual size with direct imaging and radar and laser ranging, not just from transit depth. That gives you a precise radius. With those two, you recompute the density locally and see if the original model holds. If the in-system density still comes out high, close to Earth's or above, you're dealing with a solid metal and rock planet. If it drops and looks more like a lower density body wrapped in a thick envelope of hydrogen and helium, then a lot of the reason you came here just evaporated. The first big reality check is, did we even classify this planet correctly? Or did the long trip start with a wrong assumption? Once you trust the mass and radius, the next thing is much more personal. What does gravity on this planet actually feel like to your body? On this world, with around 2.5 times Earth's mass but only about 1.3 times the radius, the surface gravity works out to roughly 1.5 times Earth's. In other words, about 15 meters per second squared, instead of Earth's 9.8. If you weigh 80 kilograms on Earth, about 176 pounds, you'd effectively weigh around 120 kilograms here, about 265 pounds. That is not a small change. Every step loads your bones and joints harder. Your heart has to work more to push blood up against that stronger pull. Standing up is harder. Running is exhausting. Lifting anything feels like it's glued to the ground. Vehicles need more thrust to take off, more fuel to land softly. Buildings and towers can actually be shorter for the same structural limits, because the weight on every beam is higher. You have to ask hard questions. Can unmodified humans live long-term at 1.5 G without serious health problems? Or do you need biological tweaks, exoskeletons, or strict time limits on surface work? Training people for this gravity becomes as important as training them for radiation or vacuum exposure. A habitable planet with the wrong gravity might be technically landable but practically hostile to human bodies. Even if your muscles can handle it, that still doesn't tell you whether the place is warm, cold, or lethal. So the next problem is critical. Is this planet actually habitable? Or is the habitable zone label misleading? From far away, you called this world promising because it sits in the star's habitable zone, the range of distances where liquid water could exist on a surface, given the right atmosphere. But the real surface temperature isn't set by distance alone. It depends on how much light the planet reflects, its albedo, and how strong its greenhouse effect is. Earth, for example, would sit at about -18 degrees Celsius, 0 degrees Fahrenheit, if it had no greenhouse gases, frozen solid. Our actual average surface temperature is about 15 degrees Celsius, around 59 Fahrenheit, because water vapor, carbon dioxide, and other gases trap heat. Now think about Venus, closer to the sun, covered in thick carbon dioxide clouds. Its surface is around 420 degrees Celsius, almost 800 Fahrenheit, hot enough to melt lead. Your exoplanet might be in a comfortable orbit, but wrapped in Venus-style clouds that push the surface into oven territory. Or it might have a thin, clear atmosphere, low greenhouse power, and sit near the freezing point. To find out, you scan it in infrared, you measure the energy it emits, you watch how much heat it loses on the night side, you track day-night temperature contrasts. From that, you find an effective temperature, what the planet would have without greenhouse gases, and then the actual surface temperature. The difference tells you how strong the greenhouse is. Thick carbon dioxide and high-level clouds that trap heat will push you out of the walkable range fast. A thin, mixed atmosphere might keep things in the liquid water window. This is where habitable zone stops being a label in a paper and becomes an actual climate you have to live in. Suppose the temperatures look survivable. That still leaves a major question. What kind of surface are you dealing with? Ocean world, ice shell, or dry rock? From orbit, you switch to mapping mode. Radar altimetry measures surface height, showing you whether there are deep basins and shallow plains. Microwave and infrared sensors look at how the surface absorbs and emits radiation. Water, rock, and ice each have distinct signatures. Combining those, you can tell how much of the surface is covered by liquid water, how much by land, how much by ice. On Earth, about 71% of the surface is ocean. If this new world is 90% ocean, with only scattered small continents or islands, colonization shifts towards floating cities, platforms, and underwater habitats. You worry more about storms, currents, and wave energy, less about farming soil on broad land masses. If instead the world is mostly land with only small seas and lakes, you may be looking at a global desert with water locked underground or at the poles, a Mars Plus situation where you drill, mine, and pipe water over long distances. Ice coverage matters too. Thick polar caps or global ice shells change how easy it is to get at liquid water and how stable the climate is. An ocean under ice, like a scaled-up Europa, could hide a vast, shielded environment, but also make direct surface colonization harder. The exact layout of oceans, ice, and rock sets the basic strategy for any long-term human presence. Once you understand gravity, temperature, and surface layout, you can finally zoom out again and ask a bigger, more unsettling question. Is this planet typical, Or is it breaking the patterns we thought we understood from Kepler and other surveys? The Kepler and TESS missions showed that small, rocky planets are common, that hot Jupiters are rare, and that super-Earths and mini-Neptunes fill a wide range of sizes and densities. We built statistical models, linking a planet's radius and mass to a likely composition. Your target planet was one of those data points, a super-Earth in the right zone, with a density that looked normal for rock. If your close-up measurements match the predictions, if the composition, atmosphere, orbit all fit neatly, then this planet becomes a confirmation, a strong checkmark on our models. It tells you that the mass-radius relationships and climate expectations we built from faraway data actually hold, at least in this case. That boosts confidence when we look at other systems still out of reach. But if this planet turns out strange, for example, if it has a much thicker gas envelope than expected, or an atmosphere that doesn't match its mass and irradiation, or climate behaviour that doesn't line up with standard greenhouse physics, then you have something very different. One weird planet, studied in detail, can force you to adjust how you interpret thousands of light curves. Maybe we've been misclassifying whole categories of worlds. Maybe certain combinations of mass, radius, and temperature produce outcomes we didn't predict. Either way, the entire exoplanet catalogue back home now has to be viewed in light of what you see here. This single world, the one that pulled you across 4 light years, either confirms that our picture of planets is mostly right, or it blows a hole straight through it. And even if this planet is perfect on paper, you're still not safe yet. Because to actually work with it, or land near it, you first have to drop into orbit without dying. So the next problem hits hard. After 100 years of travel, and all this precious data, how do you insert into orbit around this pretty blue marble without missing it or crashing straight into it? You've crossed light years and survived the braking phase, but now you hit a new hard limit. The planet does not care how long you waited. It only cares about your exact velocity and position right now. To get into orbit, you have to match the planet's motion around its star. For an Earth-like orbit, at about 1 astronomical unit, the planet is moving at roughly 30 kilometers per second, around 19 miles per second. If you arrive from interstellar space still carrying tens of kilometers per second of relative speed, you need precisely timed burns to bring that relative speed down to the tiny difference between your trajectory and the planet's orbital path. Here, a small mistake is huge. A 1% error in velocity, when you are dealing with tens of kilometers per second, is hundreds of meters per second off target. That is enough to drop your periapsis, your closest approach, too low, so that you skim into the upper atmosphere and burn hard, or break up, or too high so that gravity only bends you a bit and then you are flung back out of the system. After 100 years of flight, a fractional percent slip in the final minutes can erase the entire mission. There is no real-time rescue from Earth. Your insertion sequence is pre-planned and supervised only by onboard systems. Thrusters have to fire for exactly the right duration, in exactly the right direction, taking into account fuel slosh, engine wear, and asymmetries in the mass distribution of the ship. Guidance software must correct for small deviations on the fly. Every sensor reading, every micro-correction matters. Even if you plan to slow down well before you get this close, you still look for free help inside the system, which leads to the next tool in your kit. Can you use the local gas giants as engines? Gravity assists are standard in our solar system. Probes dive past Jupiter or Saturn, and their paths get bent and their speeds change without burning much fuel. In your new system, any massive gas giant is a potential source of free delta Vs. By flying a close pass behind or ahead of such a planet, you can rotate your velocity vector by tens of degrees and change your speed by several kilometers per second, cutting down what your engines need to do. But the price is precision. To get a useful assist, you must hit a specific altitude and track through a narrow corridor above the atmosphere. Too high, and the bend is small, you waste the opportunity. Too low, and you slam into dense atmosphere or end up deep inside intense radiation belts. Those belts can wreck electronics and dose any crew with huge amounts of radiation in hours. Your navigation system has to target a window, maybe a few tens of kilometers thick, while approaching from hundreds of millions or billions of kilometers away, at interstellar speeds. The timing has to match the giant's orbital position as well, because you need the right relative geometry between you, the planet, and the star. You are trading propellant for math, and the math is unforgiving. On top of trajectory accuracy, there is another physical limit you cannot ignore during these close passes. How much tidal stress can your ship actually survive? Tidal forces are just differences in gravity from one end of the ship to the other. Near a massive body, the side closer to the planet or star feels a stronger pull than the far side. Over a 100-meter-long hull, that difference can become serious if you dive too close. The structure then feels a stretching and bending load along its length. Around extremely dense objects like a white dwarf with roughly Earth's radius but close to the Sun's mass, those gradients can be extreme. Even around a large gas giant, getting very close can create tidal accelerations that add up to fractions of a g or even multiple g from bow to stern. That means some parts of your frame are being yanked harder than others, and the internal supports have to carry that load. If those tidal forces exceed your structural safety margins, beams can deform, trusses can crack, and rotating sections that provide artificial gravity can be thrown out of balance. You solve this by setting strict minimum approach distances for different types of bodies. You might accept higher loads for a short time to get a strong assist, but you calculate exactly how much the hull can take over that interval. There is always a tension. The closer you go, the more free speed change you get, but the higher the risk of physical damage. Let's say you survive braking and any assists, and now your speed relative to the target planet is finally down in the tens of kilometers per second range. The next challenge is choosing the kind of orbit you actually drop into and how you turn that into something stable. Your first capture into orbit will usually be very elongated. You fire your engines or use aero capture so that your path just transitions from a hyperbola, an escape trajectory, into an ellipse, a bound orbit. The periapsis, the low point, may skim close to the planet, while the apoapsis, the high point, can stretch out millions of kilometers. This is similar in concept to orbits used by lunar and Mars missions, but your initial approach speeds and energies are far larger. On each pass through periapsis, you have options. You can fire engines to lower apoapsis. You can use small dips into the atmosphere. Controlled aerobraking to bleed off speed, or you can adjust your inclination, the tilt of your orbit, to line up with the planet's equator or a particular landing site. You repeat this over many orbits, slowly circularizing until you have a near-circular, low orbit that is safe for long-term mapping, relay work and lander deployment. You also need to avoid orbital resonances with large moons that could periodically pump up your eccentricity and destabilize your path. You simulate years or decades ahead, checking that your chosen orbit will not drift into the atmosphere or into a collision course with a moon. Once you're finally in a clean, reliable orbit, with the planet below you and the star above, your role in the system changes. You're no longer just a visitor dropping in once. You are now the reference point that defines here for every ship that comes after you. So the next crucial step is, how do you turn your position into a navigation grid for an entire new solar system? Now that your orbit is well known, you can start broadcasting. High-precision radio beacons and laser pulses go out on known schedules. Other spacecraft, now or in the future, can pick up those signals and triangulate their positions. You run laser ranging to moons, large asteroids, and possibly other orbiters, timing how long it takes light to bounce back. That builds an extremely accurate 3D map of where everything is and how it moves. You track tiny irregularities in the planet's motion to refine its mass and gravitational harmonics. You log the exact orbital periods of moons. You apply relativistic corrections to time signals so that clocks on different orbits stay synchronized. Piece by piece, this becomes a local equivalent of a GPS network, not just around one planet, but extended out to other planets and major bodies, linked by your timing and ephemeris data. Future starships will arrive decades or centuries from now into a system that already has this grid. They will not have to solve the full navigation problem from scratch at interstellar speeds. They can lock onto your descendants' beacons, adjust earlier, and take safer paths. Your success or failure in these first hectic months sets the baseline risk for every later mission. And now with the ship finally stable in orbit and the navigation math under control, a new layer of danger and opportunity opens up. because below you there is an actual sky, with real air, weather, and chemistry that your crew might one day have to breathe. So the next question is direct. When you look down through that atmosphere, are you seeing a place humans can ever walk? Or a beautiful, toxic trap? You're in orbit, looking down through an atmosphere that might kill you in seconds or keep you alive for generations. And the first basic question is simple. What is the pressure at the ground? On Earth, surface pressure is about 1 bar, around 101,000 pascals. That's the baseline your body is built for. Mars is down at about 600 pascals, around 6,000ths of a bar, so thin that liquid water boils away and unprotected humans black out and suffocate almost immediately. Titan, Saturn's big moon, sits at about 1.5 bar, 50% higher than Earth. You could walk there in a pressure suit that doesn't even need to be rigid, even though the air is nitrogen and methane and far too cold to breathe. Your target planet could be in any of those regimes, or far beyond. If your instruments report 5 bar at the surface, that's 500,000 pascals, like being 40 to 50 meters underwater on Earth, about 130 to 160 feet. Submarines and diving suits handle that easily, but an unprotected human would be crushed inward, ears bursting, lungs in danger, blood under intense stress. Life support systems, lander hulls, seals, all have to be rated for that load. At the other extreme, if pressure is 1/10 of a bar or less, your saliva and tears start to boil away, and you need a full pressure suit just to keep your body's fluids in the right state. Habitable here doesn't just mean temperature and chemistry. It means you can keep a normal human body in one piece without extreme engineering. Until you know the number, from direct measurements, you treat the surface as hostile by default. Once pressure is pinned down, you still don't know whether the air is safe to breathe. So the next step is clear. What exactly is in this atmosphere, molecule by molecule? Breathable air is not just has oxygen. Earth's air is about 78% nitrogen, 21% oxygen, and a small fraction of carbon dioxide and other gases. That mix gives you enough oxygen for metabolism without turning the whole planet into an instant fire trap. Change those ratios and everything changes with them. If your lander's gas chromatograph and mass spectrometer report 40% oxygen, that might sound great for breathing, but it's bad news for flammability. Materials that are barely flammable on Earth can ignite easily and burn extremely fast at those levels. Spacecraft, habitats, even dust and clothing become bigger fire risks. If carbon dioxide is at several percent instead of a few tenths of a percent, unprotected humans will hyperventilate and risk blood acidification. Low levels of toxic gases like hydrogen sulfide or nitrogen oxides, even at parts per million, can damage lungs and nervous systems over time. Your instruments don't guess. They sniff samples and return exact molar fractions for nitrogen, oxygen, argon, carbon dioxide, and methane, water vapor, and dozens of trace compounds. From that list, you can say whether the air is directly breathable, whether it needs partial scrubbing, or whether it's completely unusable and must be kept out of habitats at all costs. The difference between we need masks and we need full suits and bulkheads is written in those numbers. Even with a survivable mix, the air is not static. It moves, it organises into patterns, and those patterns control where you can safely land and build. So the next issue is, what kind of weather machine are you dealing with? From orbit, radiometers and spectrometers scan the planet in multiple wavelengths, tracking temperature at different altitudes, cloud tops, and water vapor. Over a few days, you can watch how clouds move, how storms grow and decay, and how heat flows from equator to poles and from dayside to nightside. On a fast rotating world, similar to or faster than Earth's 24 hours, the Coriolis effect breaks the atmosphere into multiple bands. You get jet streams like Earth's mid-latitude jets and storm tracks that follow them. That can mean predictable storm zones and clearer belts, useful when choosing landing sites and flight paths. On a slow rotator, with long days and nights, air may flow more directly from the hot day side to the cold night side, forming 1 or 2 giant circulation cells. That can mean extreme temperature swings and massive, slow-moving weather systems. You look for permanent storm bands, huge hurricanes parked over warm oceans, dry zones where descending air suppresses clouds, and polar vortices that trap cold air. All of that tells you where flying is safe or dangerous, where surface bases risk constant storms, and where resource extraction, like mining or farming, might actually be stable over time. But the sky is more than just wind and clouds. Suspended particles, hazes, and chemical smogs can change both the climate and the chemistry of any life that evolves there, or any humans who try to live there. So the next question is, what's actually hanging in this air? On Titan, thick orange haze formed by ultraviolet light breaking apart methane and nitrogen creates layers of organic particles. On Venus, you have clouds of sulfuric acid. On Mars, superfine dust stays airborne for months, spreading planet-wide and coating everything. Your new world could have any of these, or a mix. To find out, you fire LiDAR, lasers that send pulses down and time the reflections, building profiles of how dense the aerosols are at different heights. You measure optical depth, basically how much light gets scattered or absorbed as it passes through the air, at many wavelengths. Smaller particles scatter shorter wavelengths more, giving you clues about their size. Ultraviolet spectrometers look for photochemical products, molecules created when high-energy light breaks simple gases apart and lets them recombine in more complex ways. Thick hazes can cool the surface by reflecting sunlight or heat it by trapping infrared, depending on composition and altitude. Dust loads can make solar power unreliable and bury equipment. Acidic clouds can corrode metal and glass. Organic hazes can act as feedstock for prebiotic chemistry or as a constant contamination risk. You can't plan long-term structures, power grids, or even basic exploration gear until you know exactly what these aerosols are doing. Even if the current atmosphere and weather look manageable, there's a deeper stability issue. A planet can have nice days now but still swing into ice ages or super hot periods on long cycles. So you have to ask, is this climate stable enough for a civilization's timescale? Or is it a trap that flips every few thousand years? Here you look at orbital parameters. How stretched is the orbit? Its eccentricity? How tilted is the axis, the obliquity? How fast does that axis wobble over time? The precession. On Earth, slow changes in these over tens of thousands of years help drive glacial and interglacial cycles, the Milankovitch cycles. They modulate how sunlight is distributed across seasons and latitudes. If your new planet has an axial tilt of 30 degrees, much higher than Earth's 23.5, seasons are more extreme. Polar regions bake in summer and freeze harder in winter. If the orbit is quite eccentric, with the planet swinging much closer and farther from its star, global energy input changes significantly over each year. Combined, those can drive climate swings that make long-term agriculture and fixed cities harder. You can infer some of this from orbital dynamics and from layered geology visible in radar and optical imaging, like repeating sedimentary patterns or ice layers. But full certainty needs long monitoring. Still, early estimates can tell you whether you're looking at a world where climate changes slowly, giving societies room to adapt, or a world that whipsaws between extremes that could wipe out early colonies. So by the time you're done with this step, you know how hard the air pushes on you, what it's made of, how it moves, what's floating in it, and how likely it is to stay within safe bounds over centuries. That answers whether you can ever walk under these skies with anything less than a full pressure suit. But there's still a much sharper question behind all this data. When you read this atmosphere's chemistry and its colours, are you seeing the fingerprints of life? Or are you about to become the first life this planet ever sees? And maybe the thing that ruins its clean state forever? You've mapped the air, the weather, the ground. Now the big question cuts through everything else. Is this world already alive? Or are you stepping into a sterile lab? From orbit, the first big clue is in the gases. On Earth, life keeps the atmosphere in a state that simple chemistry alone would not sustain. Oxygen and methane coexist, even though they like to react and cancel each other out. Nitrous oxide sits in the mix, even though it's not stable over long times without a source. If Earth's biosphere vanished, these combinations would drift back toward a simpler balance. Your instruments look for that kind of imbalance here. High-resolution spectrometers already gave you gas abundances and vertical profiles. Now you focus on combinations. Strong oxygen, not just a trace. Methane at parts per million levels or higher, not just a tiny whiff from volcanism. Maybe nitrous oxide, or other odd gases that usually come from metabolic processes. One of those alone could have a non-biological explanation. Multiple together, in the right ratios sustained over time, start to look like biology doing chemistry at planet scale. You track these gases over days, weeks, months. Does oxygen stay high while methane stays present, or does it vanish quickly? Do levels shift with seasons in ways that match growth and decay cycles, or are they tied only to temperature and sunlight, which could be explained by simple physics? From orbit you can't see microbes directly, but you can see their combined effect if they're doing enough work, even if the air hints at life. You want a second independent signal from the surface itself. So the next thing you hunt is, does anything down there change the planet's colour in a way that screams chemistry with a purpose? On Earth, plants have a very specific optical fingerprint. In visible light, they absorb a lot of red and blue, so they look green. Just beyond the red, in the near infrared, their reflectivity jumps sharply. That sudden change is called the red edge. From orbit, you can see it when you average over large, vegetated regions. It's one of the clearest spectral signs of photosynthetic life we know. Your spectrometers sweep the planet's surface at many wavelengths, not just around Earth's red edge, but across a wide band from visible into infrared, and maybe even beyond. You're looking for any similar sharp jump, at any wavelength, that's consistently tied to land masses or shallow seas. You watch how that signal moves with the seasons, growing during the local spring and shrinking during winter, or shifting with migration patterns if it's something in the water. If you find a strong spectral edge that tracks surface regions and shows seasonal or periodic changes, that's a heavy hint of some kind of large-scale pigment system, maybe alien photosynthesis, maybe something else. The exact wavelength might be different, depending on the star's light and the local chemistry, but the pattern, a sharp edge plus regular variation, is hard to get from simple rocks and ice. Those two lines of evidence, atmospheric disequilibrium and surface pigments, can push you toward a big conclusion. But they're still indirect. At some point, you want to stop guessing and actually look. So the next step is the most risky scientifically. Do you dare put instruments on the ground and go microbe hunting? Robotic landers are your front line here. They are built in clean rooms, baked and sterilized as much as possible, then sealed. On board, they carry microscopes to image any tiny structures in soil or water samples. They carry chromatographs and mass spectrometers to separate and analyze organic molecules. And they carry life detection experiments that don't assume Earth-style DNA or RNA. These life detectors look for chirality, the handedness of molecules, which life tends to bias in one direction. They look for metabolic heat, small temperature changes as microbes break down nutrients. They look for redox imbalances on tiny scales, changes in chemical energy that suggest active metabolism. We've already tested versions of these tools in extreme Earth environments, like Antarctic dry valleys and the Atacama Desert, where life is rare and stressed. On this new world, any positive signal is bigger than any previous test. If a lander shows clear microstructures that reproduce, metabolize and maintain a strong handedness in their chemistry, you're looking at independent biology. That would mean that life did not only start on Earth, it means the universe is at least twice alive. But there's a massive problem that sits in the background of every one of these tests. You are not a neutral observer. You are a contamination source. Space agencies today already take planetary protection seriously. Landers are assembled in clean rooms, surfaces are sterilized, microbial loads are tracked and reduced. Even so, hardy spores can survive in small pockets. Now scale that to a Starship that has been flying for 100 years. Microbes have had a century to hide in cracks, adapt to low-nutrient environments, ride out radiation bursts behind shielding. When you send a lander down, you have to be very sure that any life you detect did not ride there from Earth. That means strict protocols. You may keep crewed ships in quarantine orbits far away from the planet, while only pre-sterilized robotic probes touch the surface. You might use high-altitude balloons or aerostat labs that never land, only sample the upper atmosphere. You log every potential contamination event. You delay any crewed landing for years or decades until you've fully mapped what's native and what isn't. If you ignore that, you might seed a sterile world with Earth microbes, or you might alter a fragile native ecosystem before you even know it exists. Your grandchildren then inherit a mixed biosphere and can never tell which life forms are truly alien. And if you do find clear native life, even if it's just thin microbial mats on rocks or strange films in shallow lakes, the biggest problem stops being technology and starts being ethics. Now the question is, what right do you have to change this world at all? Terraforming a planet with life on it is not just engineering, it's erasing an experiment that took billions of years. Building cities, strip mining, releasing your own engineered organisms, all of that can wipe out unique evolutionary lines. You have to decide whether expanding human presence and solving your own resource and survival problems outweighs preserving a completely independent branch of biology. That's not a simple yes or no. Some will argue for strict preservation, turning the world into a protected science park, with only remote observation or small tightly controlled outposts. Others will push for selective development, choosing regions that seem less biologically rich or trying to build in ways that minimize damage. Others will argue that survival and growth of intelligent life justify large-scale change, as long as we document what was there first. Your interstellar mission, which started as a physics and engineering project, now forces a civilization-level choice. How do you treat alien life, even if it's just microbes, when your tools can reshape continents? And while you debate that, and while robots and maybe humans start working in this new environment, one more layer of risk builds quietly in the background, because all this time, your own body, and the bodies of your descendants on the ship, have been changing under a century of radiation, altered gravity, and closed-loop ecology. So now you have to turn the microscope around and ask, after 100 years, in deep space and a new gravity well, what exactly has that done to you? You crossed light years to reach this system, but your body and your culture paid for every kilometre. After 100 years, the question isn't just did the ship survive, it's what did this trip turn you into? Start with radiation. Space is not empty, it's a radiation bath. Astronauts on the ISS see about 0.3 to 0.4 millisieverts per day, roughly 10 times Earth's surface background. Over a year, that's around 150 millisieverts. Stretch that out to a century. If you were just floating in deep space with no serious shielding, you'd stack up something like 15,000 millisieverts. That's many times over lethal, cancer risk territory. So a real sentry ship has to be built like a bunker. You wrap the living areas in meters of shielding, maybe water tanks, polyethylene, or packed regolith from an asteroid. We're talking thousands of kilograms of material per square meter of hull, not thin foil. That shielding knocks down the flux of solar particles and a big chunk of cosmic rays, but not all. Some high-energy particles still punch through, producing cascades inside. You monitor dose constantly. Personal dosimeters log every spike from a solar storm. Over 100 years, you aim to keep each person's total dose down in the few hundred millisievert range, maybe comparable to, or a bit above, a career Earth radiation worker. That's not risk-free, but it's survivable. The trade-off is mass and cost. Every extra centimetre of shielding is tons of extra material you had to accelerate to a fraction of light speed. Even if radiation is under control, weightlessness is not. Microgravity wrecks bodies over months, over decades. It would be catastrophic. On the ISS, 6-month stays lead to bone losses of 1 to 2% per month in weight-bearing bones, major muscle atrophy, and cardiovascular deconditioning. That's with strict exercise routines and constant medical oversight. Over years, that trend cannot just continue. Bones would become dangerously porous, muscles would never fully recover, and balance systems would adapt to 0G in ways that make standing in 1G miserable or impossible. A 100-year mission, in true freefall, would deliver a population that can't safely walk on any planet, maybe not even in 1G habitats. So a true sentry ship almost has to spin. You build a rotating section with a radius of a few hundred meters, spinning maybe 2 to 3 times per minute. That rotation produces centrifugal acceleration that feels like gravity. At the right combination of radius and spin rate, you can simulate roughly 1G at the floor. People live, sleep, work, and raise families in that rotating ring. They visit microgravity zones only for brief tasks. You still get some odd side effects, like Coriolis forces that make moving in certain directions feel strange, and you need strong structural supports to handle the spin loads, but it's vastly better than letting your bones evaporate. Without something like that, your descendants would arrive at the target system physically fragile, like glass, barely able to function in the higher G of a real planet. Now zoom out from individuals to genetics. 100 years is 3 or 4 human generations. On a ship with only a few hundred to a few thousand people, that is a small gene pool, and small gene pools drift. In small isolated populations on Earth, random genetic drift and inbreeding can push certain traits to high frequency, including harmful recessive disorders. On a starship, the risk is higher because you can't easily bring in new people from outside. To keep the population healthy, you need active management. That probably means pairing algorithms that track family trees and genetic markers, so people who share dangerous recessives don't have children together. You might bring stored gametes, sperm and eggs frozen on Earth, as a backup injection of diversity. You might use gene editing aggressively to remove disease-causing variants from embryos. Over the decades, the genetic makeup of the ship's population shifts under a mix of random drift, deliberate selection, and adaptation to the ship's environment. By the time you arrive, human from the Starship may be genetically distinct in subtle ways from human on Earth. But it's not just your own genes that change. You are walking ecosystems. Every person on board carries trillions of microbes in their gut, on their skin, in their mouths. Those microbes face selection pressures very different from Earth. Recycled air, highly processed or synthetic diets, sterilized surfaces, rare contact with soil and animals, constant low-level disinfectants. We already see on the ISS that certain bacteria form stubborn biofilms on equipment, adapting to space conditions in ways we didn't fully predict. In a closed Sentry ship, the microbiome of the ship becomes its own evolving world. Some species will vanish. Others will adapt to plastic surfaces or water systems. Some may become more aggressive, others more cooperative. After 100 years, the mix of microbes in your crew's guts, in their water lines, in their air filters, might be as different from Earth's standard sets as any alien microbe down on the target planet. That has direct health impacts, from digestion and immune function to mental health. It also means that when you finally meet an alien biosphere, you're bringing not just humans, but a full evolved Starship microbiome into contact with it. On top of all the physical and microbial evolution, there's the mental strain. Even if relativistic time dilation shaved a bit off the clock, psychologically, a century is heavy. Most people aboard were born long after launch. Earth for them is not home I left. It's the place in the old recordings. We know from polar stations, submarines, and long-duration space simulations that isolation and confinement stress can peak in months. People get irritable, depressed, or withdrawn. Group dynamics can fracture. Now extend that to decades and generations. On a Sentry ship, kids grow up knowing that their entire world is a finite metal environment, with strict rules, limited personal space, and no outside that isn't instantly lethal. Culture has to adapt to that. You need rituals, stories, education systems, conflict resolution methods, and leadership models built for a world that never goes outside and never gets bigger, until the very end. People have to find meaning in maintaining systems they will never see finished. Some will see themselves as citizens of the ship first, of any planet a distant second. When they finally arrive at the target system, they step into a place they know first as data and simulations, not memories. So the real-time dilation is social. Earth moved on for 100 years. The ship moved on along its own path for 100 years. By the time you make contact again, you're not just physically separated by light years, you're psychologically and culturally separated by a full century of independent development. And that leads straight into the next problem. While you were changing out here, Earth was changing on its own. Technology advanced. Maybe other colonies started. When your "we made it" message finally hits home, who exactly is picking up the call? And what kind of civilization is now sitting at the other end of that 4 light-year-long radio link? You send "we're here," and the people reading it haven't even been born when you left. That's the scale you're dealing with now. Say you launched in 2125 and arrived in 2225. Earth is 100 years older, but the star is 4+ light years away. So your first arrival ping doesn't hit Earth until around 2229. Their reply reaches you around 2233. One simple back and forth takes about 8 years. That kills any idea of tight coordination. You are not a distant branch office asking HQ for instructions. You're more like a separate civilization exchanging long formal letters. Every message you send is a snapshot of your world from 4 years ago. Every message you get describes an Earth that no longer exists in its current form for you. You can still share data, discoveries, maybe even policies, but nothing is fast. You can't align elections, business cycles, or decision windows. By the time Earth reacts to your last update, you're already onto your next crisis, your next build phase, your next generation of children. Operationally, you're on your own. While that slow conversation stutters along, technology on both sides keeps moving, and it won't move at the same speed or in the same direction. Look at how fast tech already jumps. In 50 years, we went from room-sized mainframes to supercomputers in pockets. Over a full century, Earth-side AI, biotech, nanomanufacturing, and energy systems could advance so far that the ship hardware you arrived with looks primitive, more like museum pieces than cutting-edge tools. On Earth, cheap fusion, advanced quantum devices, or mature molecular manufacturing might be standard. They could build new interstellar probes that are lighter, faster, and smarter than the craft you used, and they can upgrade on every launch. You, in contrast, had to lock in most of your core engineering a century ago, at launch. But you hold a different advantage. You are sitting inside another star system. You can mine its asteroids, study its planets up close, test physics in a new environment, and run experiments Earth physically cannot. You can build tools locally that are adapted to this system's conditions. Over time, the tech tree splits. Earth may be ahead in raw computation or medicine. You may be ahead in situ resource use, extreme environment engineering, and deep space infrastructure. Now lay a law on top of that divergence, and the gap gets even sharper. Even today, international law struggles with questions like who owns the moon, who is responsible for orbital debris, and can a company claim an asteroid? It's messy, slow, and often behind reality. Add a 4-year one-way delay and a 100-year lead time, and it gets almost meaningless for daily decisions. If some committee on Earth passes a regulation in 2023 that's supposed to govern how you mine a moon or treat a local microbe, you don't even hear about it until around 2023. By then, you've already made years of choices. You may already have habitats, kids born on the surface, and industries running. For any urgent issue, conflicts, accidents, ecological mistakes, waiting years for a response is the same as getting no response. So in practice, you are sovereign. You might choose to follow Earth's frameworks as a matter of culture or shared identity, but they can't enforce anything in real time. No warships can show up in days. No court can summon you in person. Power is wherever the ability to act immediately lives. And in this system, that's you. Communication limits also throttle culture itself. Even with powerful lasers and big antennas, data over light-year distances is scarce. Beam spread and noise limit you to maybe kilobits to low megabits per second in a reliable, sustainable way. That's enough to stream compressed science data, send texts, send some images, maybe occasional videos. It is not enough for continuous high bitrate entertainment, social media fire hoses, or live interaction. That means your local culture is mostly self-generated. You can import books and shows in small batches, but you can't live in sync with Earth's trends. Music, slang, fashion, even humour drift. Kids grow up with different reference points. Your crises and heroes are different from Earth's. Over a century, that drift is like Latin splitting into French, Spanish, Italian, and so on. But with physical separation of trillions of kilometres on top. Written language may stay mutually intelligible if you work at it, but speech patterns, habits, and values will flex. After long enough, we starts to mean we here, not we plus Earth. While all that slow divergence is going on, Your mission is also quietly updating one of the biggest open questions in astrophysics, the Fermi Paradox. If advanced civilizations are easy to make, and they can travel between stars, why don't we see them everywhere? By going to another star and checking in person, you add one solid data point. If you find a system full of rocks and gas, and maybe some microbes, but no cities, no obvious probes, no loud radio beacons, that's one more nearby star where nobody built a galaxy-spanning empire. It suggests that either tech civilizations are rare, or they tend to die out, or they operate in ways that avoid obvious signals and big structures. On the other hand, if you get there and see ruins, or you pick up structured signals from the ground or orbit, or you find active technology that isn't yours, that detonates every calm theory we held, it would mean we were not the first to try this. It would raise questions about what happened to them, what their intentions are, and how many others might exist. Either way, the moment you report, "We checked this star, here is what we saw," the whole discussion about where is everybody has to change. You're not just the first interstellar colonists, you're the first serious surveyors of other people's potential neighborhoods. And whether the system is empty of minds or not, you still have to live. That means turning local matter into air, water, metals, fuel, and ardent structures. So the next hard question is, now that you're here with Earth only on the radio and no resupply ships coming, how do you strip a brand new star system for resources without wasting a century of energy? And what does economy even mean when your nearest trading partner is 4 light years away? You've got people, tools, and a whole new star, but no resupply from home. So the first hard rule is this: everything you need, you dig or build here. Step 1 is knowing what you're actually standing on and flying past. In our own system, missions like Hayabusa and OSIRIS-REx showed that asteroids come in a few key flavors. Some are carbon-rich, dark rocks loaded with organics and sometimes up to about 20% water by mass. Some are stony with silicates and a bit of metal. Some are metallic, mostly nickel-iron, basically chunks of planetary cores. In this new system, your spectrometers start from orbit, scanning the belts and families of rocks. Infrared signatures tell you which bodies are water-rich, which look carbonaceous, which have the bright reflective look of metal. Radar gives you shape and rotation. You pick a sample set, send landers or small probes, and do touch-and-go sampling like OSIRIS-REx. But now as a routine industrial step, you're hunting for 3 main things: nickel-iron bodies for structural metals, volatile-rich comets and icy rocks for water, and simple gases which become propellant, air, and radiation shielding. Carbonaceous rocks for organics, feedstock for chemistry, and maybe agriculture. Once you know the mix in the local belts and near-planet regions, you can say where the first serious mines make sense. But composition alone doesn't decide your first targets. The real cost is speed change. Delta So the next question is, how expensive is, in meters per second, to get from your main base to those resources? In the inner solar system, going from low Earth orbit to many near-Earth asteroids costs only a few kilometers per second of delta V. With efficient drives, that's well inside practical limits. In your new system, you build the same kind of map. For each candidate moon, asteroid, or comet, you compute the velocity changes needed to reach it from your hub orbit, land or dock, lift off again, and return. That gives you a subway map of the system, where each route is labelled not in minutes, but in meters per second of speed change. Shallow gravity wells, like small asteroids or small moons, are cheap stops. Deep wells like big planets are expensive. Your propulsion tech sets the budget. A high-efficiency fusion or advanced electric drive can throw around several kilometers per second without going broke. A lower performance system forces you to be pickier. In practice, your early industry clusters around places with low delta V cost and high value. That might be a metal-rich asteroid in a near-circular orbit close to your main station, or an icy moon that's easy to reach and provides water for both life support and fuel. Over time, this delta V landscape becomes the real cost of living index for the system. Cheap routes get crowded, expensive wells become special-purpose destinations. All that mining and moving only works if you have serious energy to run it. So the next constraint is, how much usable power can you actually pull out of this star, here and now? at 1 astronomical unit from a sun-like star, the raw solar power falling on each square meter is about 1,360 watts. If your solar panels are 20% efficient, each square meter gives you a bit over 200 watts. Scale that up. A square kilometer of panels, 1 million square meters, produces around 270 megawatts in full sunlight. That's a small city's worth of power from one patch of collector. Move closer to the star, and that power increases with the inverse square of distance. At half an astronomical unit, you get 4 times as much per square meter. Farther out, it drops. So you place big solar farms where the flux is good, balancing thermal stress on the hardware against raw output. You park them in stable orbits or on airless bodies with good sunlight, and beam power by microwave or laser to where it's needed. You also likely bring compact nuclear reactors, fission at first, maybe fusion if it's mature by your launch date. Small modular reactors, the kind already being prototyped on Earth, can give tens to hundreds of megawatts in a compact package, day and night, regardless of weather or dust. Those go on stations, mines in shadowed craters, and ships operating far from strong sunlight. With solar farms plus reactors, you build an energy base that can melt regolith, refine metals, drive big life support systems, and power heavy industry. Without that, your colony is stuck at a camping scale forever. Now, once you're pulling in metals and power at industrial levels, the old instinct kicks in. Can you sell any of this back to Earth? The blunt answer, at least early on, is no. Even if you're mining platinum by the cubic kilometre, a 4 light-year shipping lane is a terrible business route. The transit time is on the order of a century each way for bulk cargo if you don't want to vaporize your ships. The energy cost to accelerate and decelerate heavy loads to a decent fraction of light speed is enormous. Near-Earth asteroids and moons offer the same materials with far shorter and cheaper trips. So physical exports make no economic sense at first. Your real export is information. Detailed maps of another star system. High-precision tests of stellar physics, planetary formation, and extreme materials behavior. If there's alien life, that data is priceless on the scientific and cultural level. You send back discoveries, not awe. Earth sends back designs, software. Maybe genetic tools. Interstellar trade looks more like a data exchange between two research superpowers than like container ships full of goods. Meanwhile, you still have to decide where your own people live. And that brings up a huge fork. Do you try to rewrite an entire planet to suit human biology? Or do you build habitats that give you what you need right away? Terraforming a whole planet is orders of magnitude harder than anything we've done. Mars studies already show that thickening an atmosphere, warming the surface, and protecting it with a magnetic field are all enormous energy problems. You'd have to release and process billions of tons of gases, maybe redirect comets, maybe build gigantic orbital structures to deflect radiation. That's a project that runs on timescales of centuries to millennia, with no guarantee you don't break something you care about along the way, especially if native life already exists. Building habitats in space is different. Take a cylinder 2 kilometers long, maybe a couple of 100 meters in radius. Spin it so the inner surface feels roughly 1 g. The inside area is on the order of a dozen square kilometers, about 5 square miles, one mid-sized city's footprint. Wrapped into a tube, you control air temperature, light cycles, radiation and gravity. That's a hard engineering job, but it scales from things we already understand. Space station modules, rotating habitat designs, the behavior of lunar dust and regolith for shielding. You can build one habitat, learn from it, then build 10, then 100, maybe using asteroid metal and regolith as raw material. If one fails, the others keep going. You can place them wherever the delta V map is favourable, near resources or at stable points for communication. Physics clearly favours habitats as the first, fast step, and terraforming as a slow second-order change, if you ever choose to do it. The data from our own system, from ISS to lunar concepts to Mars climate models, all point the same direction. It's easier to make many small, artificial Earths than to rewrite a whole alien one. Once you're running mines, power farms, and habitats, you've started turning a random star system into a structured human environment. The next escalation is obvious. With more and more power collectors around the star, at some point you stop thinking in terms of mines and domes and start thinking in terms of star-scale engineering. So the next question is, when you finally have the tools and energy, how far do you push? Do you start turning this star itself into your power plant? You've got mines, habitats, and huge power farms, and at some point the obvious next step appears. Stop thinking in gigawatts, start thinking in fractions of a star. A full, solid Dyson sphere is basically fiction. But a Dyson swarm, thousands or millions of separate collectors in orbit, is just an extension of solar power satellites we already understand. At about 1 astronomical unit from a sun-like star, the total output is around 4 times 10 to the 26 watts. If you capture even 1/100th of 1% of that, you're still grabbing roughly 4 times 10 to the 21 watts. For comparison, all of humanity today runs on something like 2 times 10 to the 13 watts. So with a very small geometric slice of the star's output, you get power that's billions of times current human use. The underlying physics doesn't change. It's still orbital mechanics, solar panels, radiators, transmission beams. What changes is scale and automation. You're not launching one satellite at a time from a planet. You're using robotic factories on asteroids to churn out collectors by the thousands, maybe millions, and nudging them into precise orbits. These collectors can be simple mirrors, photovoltaic panels, or heat engines that dump waste heat in controlled directions. You place them in many different orbits, forming a loose, dynamic cloud around the star. Power can be used locally, turned into beams to feed habitats, or stored chemically. The main limit isn't sunlight, it's the raw material to build the hardware. That brings you to a brutal constraint. Does this system actually have enough metal and other resources in the right places to support a serious swarm? To build a large Dyson-style infrastructure, you need staggering amounts of stuff. Advocates sometimes talk about dismantling a Mercury mass planet, roughly 3.3 times 10 to the 23 kilograms, and spreading that material into thin collectors a few millimeters thick. In theory, that could give you trillions of square kilometers of panel area. In practice, you start with what the system gives you. Your detailed surveys of the asteroid belts, moons, and inner rocky planets tell you the composition breakdown. If there's a Mercury-like inner planet rich in metals, or dense metallic asteroids, you have a good base. If instead the system is poor in carbon, poor in easily accessible metals, and rich only in silicate rock, you hit limits quickly. You can still build, but your collector swarm may stay relatively sparse, constrained by the available aluminum, iron, copper, and carbon for structural members, conductors, and panel substrates. Every ton of metal you turn into a collector is a ton you don't turn into a new habitat or a ship. You have to decide how much of the system's solid material you're willing to convert into thin infrastructure around the star, and how much you leave in planets, moons, and stations. While you scale up, there's another side effect you can't ignore. You start looking exactly like the kind of alien civilization we've been searching for from Earth. Infrared telescopes back home already look for stars that are unusually dim in visible light, but bright in mid-infrared. The idea is simple. If a civilization covers its star with collectors, the star's energy still has to go somewhere. It gets turned into waste heat, glowing in infrared. So far, we haven't seen clear, strong examples of that. Once you build even a modest Dyson swarm, you produce that waste heat signature yourself. To distant observers, your star will look a bit dimmer in visible light, and a bit brighter in certain infrared bands than a bare star of the same type. From your side, you can measure exactly how bright that signature is at different build-out stages. Then you compare that to the sensitivity of surveys Earth has already done. If your early swarm already would have lit you up in those surveys had you been in someone else's sky, then the fact that we haven't seen many such signatures suggests that large, power-hungry civilizations are rare, or they don't build visible swarms. If your swarm has to be insanely large before it becomes detectable at interstellar distances, then our null result says less. Either way, you've turned yourself into a live test case for SETI theories. But making a star-wide power grid isn't just launch more panels. It's also a traffic and debris nightmare. So the next hard reality is, can you keep this orbital shell from turning into an unmanageable junk field? We already know about Kessler syndrome in low Earth orbit, the idea that too much debris can trigger chain reaction collisions, filling orbits with shrapnel and making them unusable. A Dyson swarm multiplies that risk by orders of magnitude. You're talking about thousands, maybe millions of separate units, each with its own orbit, station-keeping system, and failure modes. You need strict orbital management. Collectors get assigned specific lanes and inclinations, with built-in collision avoidance. You track every piece of hardware and every chunk of debris. End-of-life plans are mandatory. A dead collector must move to a safe graveyard orbit, be deorbited into the star, or be physically recycled. If you ignore that, a few uncontrolled collisions can produce swarms of fragments that threaten not just other collectors, but also habitats, shipyards, and transit traffic near the star. Software, sensors, and constant small thrusts become the air traffic control of a system-scale power net. The larger you build, the more you're managing an information and control problem, not just a construction job. Once you've mastered that, you reach the point where you simply have more power than you know what to do with locally. That makes the next idea tempting. Can you actually send some of this star's power back to Earth? Interstellar power beaming sounds like magic, but the limits are harsh. You can use microwaves or lasers to send energy. The main problem is divergence, beams spread out over distance. Even if you use a transmitter array a kilometre wide, after a few light years the spot is enormous, billions of kilometres across. The receiver on the other side, maybe a huge rectenna array in the outer solar system, only intercepts a tiny fraction of the beam. Still, with enough power on your end, that tiny fraction can be large in absolute terms. You might aim a narrow laser from this star to a known receiving area in the outer regions of the home system, not the inner planets where safety margins are bigger. A gigawatt or a few gigawatts delivered into a massive collector ring around Jupiter or beyond could, in principle, supplement local power. It won't be the main energy source for Earth, but it would be a proof that systems can literally light each other across light years. Doing this safely is non-trivial. You must guarantee beam pointing accuracy so you don't fry unintended targets. You need fail-safes so the beam shuts off if the receiver goes out of alignment. You need treaties with Earth so everyone agrees what is being sent, when, and where. But if you get it working, it closes a loop. Your arrival in this system and your build-out of megastructures eventually changes the energy budget back home. And by the time you can do all of this, you're running observatories and factories around at least 2 stars with enormous baselines and ridiculous power for instruments. That changes astronomy itself. So the next step is obvious. Once you have full-scale labs in 2 separate solar systems, what does that do to our maps of the galaxy, our measurements of the universe, and even our tests of the basic laws of physics? You've turned one star system into a lab, but the real upgrade hits when you add a second lab 4 light years away. Now you're not just looking at the universe, you're measuring it in stereo. Right now, space telescopes like Gaia use Earth's orbit as a measuring stick. Over 6 months, Earth moves from one side of the Sun to the other, about 2 astronomical units apart, roughly 300 million kilometres, about 200 million miles. That baseline lets us measure tiny shifts in star positions, on the sky, parallax, and from that, distances. Drop a second observatory 4 light years away, and your baseline explodes. 4 light years is on the order of 40 trillion kilometres, about 25 trillion miles. You've just multiplied your parallax ruler by about 100,000. Angles that were far too small for Gaia to see suddenly jump into the measurable range. Stars in distant clusters, nearby galaxies, and far corners of our own spiral arms shift differently against the background as seen from these 2 points. With that enormous separation, you can nail their distances with far smaller error bars. That cascades into everything else. Because most astronomical numbers, from how bright a star really is to how massive a cluster is, depend on distance. Tighten those, and entire models of stellar evolution and galactic structure snap into sharper focus. So once you have 2 vantage points measuring distances this well, the next natural step is, can you finally build a true 3D, moving map of the galaxy around you, not just a flat star chart? From one system, you can see motions on the sky and radial velocities from Doppler shifts. But it's like trying to understand a freeway system from one overpass. From two systems, separated by light years, you can triangulate much more cleanly. You use both ends to time pulsars, those spinning neutron stars that flash like ultra-precise lighthouses. Tiny differences in arrival times tell you where they sit in 3D space. You map neutral hydrogen gas with radio telescopes in both systems, watching how clouds of gas move along the spiral arm, how they collide and compress, and where star formation is actually happening right now. By comparing star motions and gas flows, as seen from both locations, you can watch how material streams along the arm, where it turns, where it piles up in density waves, and how those waves trigger new stars. What used to be a rough model of our spiral arm structure becomes an actual kinematic map, with depth, velocity fields, and shock fronts all charted. But that's just the start. Once you have observatories and serious power in two separate systems, you can do more than map stars and gas. You can start using the galaxy itself as a lab for extreme gravity. That raises a sharp question. What happens when you measure gravitational waves with a baseline not of thousands of kilometers, but of light years? Today's detectors, like LIGO and Virgo, use baselines of a few thousand kilometers between facilities. When a gravitational wave from merging black holes passes by, it hits each detector at slightly different times and with slightly different amplitudes. From those differences, we triangulate the source's position in the sky and test general relativity. Put a gravitational wave detector in your new system and sync its clocks with Earth's detectors as well as you can, and suddenly your baseline jumps from thousands of kilometers to tens of trillions of kilometers. The same wavefront that sweeps past Earth also hits your remote detector years earlier or later depending on geometry. But in a way you can predict if general relativity is exactly right. By comparing arrival times and waveform shapes from light years apart, you can pin down source locations much more tightly, shrink the sky patch where telescopes must look, and probe subtle details of polarization and dispersion. If gravity behaves even slightly differently over interstellar distances than our current theory says, this is where the cracks will show. One unexpected delay or distortion, confirmed from both systems, would light up the physics community. That leads to a bigger scale question though. You're now looking at the universe from two widely separated points, both in space and in time. Cosmology assumes the universe looks roughly the same in every direction on large scales. Can you actually test that directly now, instead of just assuming it? From each system, you can measure the cosmic microwave background, the faint afterglow of the Big Bang. You can count galaxies in deep surveys, and you can measure how fast distant galaxies recede, which feeds into the Hubble constant and dark energy models. With two observatories separated by light years, you can compare these numbers. If the universe is truly homogeneous and isotropic on large scales, the CMB spectrum should be the same, after correcting for local motion. Galaxy distributions should match what you'd expect from statistical noise. The expansion rate, the Hubble constant you infer, should agree within error margins. If they don't, if one system sees a slightly different expansion rate, or a small but consistent bump or dip in the CMB power spectrum compared to the other, that would mean our simple same everywhere assumption breaks. Even a small mismatch, persistent after careful checks, would push us toward new ideas. Large-scale cosmic structures we didn't account for, anisotropic dark energy, or something even stranger about space-time itself. You've turned your colonization mission into a cosmology experiment. Underneath all these huge measurements is one more precise, almost surgical test. You now have clocks, lasers, and atoms ticking away in two different corners of space, linked by light. So you can ask a very sharp question. Are the fundamental constants of physics actually constant over light-year scales and over a century of time? On Earth, atomic clocks already keep time to better than a nanosecond over days. You can put similar or better clocks in both systems. You sync them using laser links and pulsar timing as best as physics allows. Then you keep comparing. You look at well-known atomic transitions, like those used in cesium or optical lattice clocks, and you check whether their frequencies drift relative to each other over time and distance. You also compare precise spectral lines from distant quasars and galaxies, seen from both systems. If the fine structure constant, which controls how strongly electrons interact with light, or other constants are truly fixed, then within instrumental noise you see no drift. If they change even by a tiny fraction, over light-year baselines or over the 100 years of your voyage, plus settlement, those changes will show up as systematic shifts. Finding a real drift would be one of the biggest discoveries in physics, telling us that the laws of nature are not perfectly uniform in space and time. Even confirming that they are rock solid within very tight limits is a big deal, because it closes off whole families of speculative theories. So by just existing in two star systems at once, with good instruments and clear communication, you're not only colonizing space, you're rewriting textbooks back home. You're tightening distance scales, mapping the galaxy in 3D, stress testing general relativity, probing cosmology, and checking the stability of physical law itself. Which leaves one last very human scale question hanging over all of this. After you've spent a century getting here and built all this hardware and knowledge, do you ever actually go back to the cradle that launched you? Or is this new star the place where your branch of humanity stays for good? You've built habitats, mines, observatories, and a whole new society around another star. So here's the blunt question. Does anyone actually go back to Earth? Or is this a one-way move forever? Start with the basic physics, Bill. To get here, you took a ship of roughly 1,000 tons, about 1 million kilograms, and pushed it up to around 0.2 times light speed, then killed that speed at the other end. The total kinetic energy involved was on the order of 10 to the power of 21 joules. That's so far above present human energy use that it's hard to compare. Doing a full round trip at similar speeds doubles that, Bill. You need another 10 to the 21 joules to accelerate a ship back toward Earth, and another huge chunk to slow it down again when it arrives. Now compare that to what you can do with the same energy locally. That amount of energy could build giant new habitats, full industrial belts, or whole constellations of telescopes and collectors. It could expand your local civilization in ways that feed millions of people and drive centuries of science. Sending a handful of people, or a symbolic return mission, back to Earth starts to look like a luxury, or even a waste. So unless Earth has something uniquely valuable that this system absolutely cannot supply, the raw math encourages you to stay put. Early on, interstellar transport is a rare, strategic move, not a casual option. A ticket home is measured in exajoules, not dollars. Even if you somehow pay that energy cost, there's another problem waiting for you at the other end. Your own biology is no longer tuned for Earth. After a century, your population is adapted to two environments. First, to the artificial world of the ship and habitats, with controlled air, controlled light, and possibly slightly tweaked artificial gravity. Second, to the new system's planets and moons, which might have gravity higher or lower than Earth's, different day lengths, different radiation levels, and different spectra of starlight. Muscles, bones, cardiovascular systems, even circadian rhythms all adjust to what they live in. Someone raised from birth at 1.3 or 1.5 G will have a different baseline than someone raised in 1 E. Someone whose skin and eyes grew up under a cooler, redder star, or behind specific UV filters, will respond differently to the sun's spectrum. Then there's the invisible layer, pathogens and microbiomes. Your immune systems have learned to deal with your local ship and colony microbes, not Earth's current mix, after another century of evolution. Landing back on Earth could feel as extreme for you as Mars does for people today. Gravity might be slightly off from what your reflexes expect. Sunlight and UV could trigger new issues. Your immune system might overreact or underreact to Earth bacteria and viruses. Even if modern medicine can buffer some of that, it won't be a casual vacation. A short visit in a controlled environment might be possible for the rich or the scientific elite. A full repatriation, live and die on Earth, will be rare. Face that reality and the path that actually makes sense starts to shift. Instead of moving bodies across light years, you move information. Once both systems have serious infrastructure, the most efficient traffic between them is bits. You can send genetic sequences, AI models, engineering designs, novels, music, news, scientific papers. A data stream beams across at light speed. A 4-year transit one way, but carrying the equivalent of entire libraries. If mind uploading or advanced neural recording becomes mature technology, even people might travel as information. A copy of a brain's structure and state, transmitted as a dataset, could, in principle, be instantiated in a synthetic body or a simulated environment on the other side. That raises its own ethical questions about identity and continuity, but from a physics standpoint, it's far cheaper to move petabytes than megatons. The pattern looks familiar. Even today, global trade is shifting more toward information and services than bulk cargo. For interstellar links, that imbalance becomes extreme. Coal, metals, food, and water are local. Ideas, algorithms, culture, and maybe digital minds are what actually cross the void. While that's happening, your sense of home is changing too. After a few generations, are you a traveller or are you simply from here now? Studies of migrant communities on Earth show a consistent trend. The first generation sees themselves as having left home. The second generation feels pulled both ways. The third and later generations mostly see their birthplace as home and their ancestors' land as heritage, not destination. On a starship and in a distant system, that effect is amplified by distance and time delay. For your grandchildren and great-grandchildren, Earth is the place in lessons, in old footage, in stories. The gravity they grew up in, the star they see out the window, the habitats they walk through, that's their real environment. Their loyalty, their memories, their friendships are all tied to this new well, this system's planets and stations. Going back to Earth for them is like us talking about going back to the Paleolithic or back to the Roman Empire. It's a concept, not a plan. That shift in identity feeds back into the physics argument. If almost nobody actually wants to leave their birth system, investing ridiculous energy to send people home makes even less sense. The ones who do travel may be explorers, diplomats, or scientists, not mass migrants. For everyone else, this system is not a destination. It's just where life is. Put that together, and you see a pattern we've already lived once, on oceans instead of stars. In early ocean exploration, many voyages were one way. Settlers left Europe for the Americas or the Pacific, and never saw their homelands again. Ships went back and forth carrying goods, letters, and sometimes a few people. But for most individuals, emigration was permanent. Only after shipping, industry, and economies matured did regular passenger travel become common. Interstellar flight will likely repeat that. In the early era, each big mission is basically a founding event, seeding a new branch of humanity in another system. Ships are rare, massive, expensive. Trips take decades or centuries. Passenger returns are exceptional. Only when you have strong industry in multiple star systems, cheap high-performance drives, and a big population that sees multi-system travel as normal, do you begin to build networks of routine interstellar travel. That's not your 100-year mission. That's phase 2 or 3, hundreds or thousands of years down the line. So for you, and for the people who arrived on this first 100-year starship, return is mostly symbolic. You return messages, not bodies. You return knowledge, not bulk. You are not round-trip passengers. You are the origin point, the first line in the family tree of a new, separate human civilization. And that brings you to the final step in this story. You left one star, you've arrived at another, you've changed your bodies and your technology, and you're not going back. So what does that actually do to humanity as a whole? To our risk of extinction? To the Fermi Paradox? To the way we think about time and the galaxy itself? So what did that one ship actually do to humanity, besides move a few thousand people from one star to another? Right now for us, the Milky Way is mostly a picture. And some statistics, about 100,000 light years across, maybe 100 to 400 billion stars. A nice background for desktop wallpapers. Once you've put humans and hardware at even one other star, that changes category. The galaxy stops being scenery and turns into physical space you can actually use. A distance like 4 light years, Proxima range, stops being an abstract very far and turns into a number you plan around. It's the light time for messages, about 4 years one way. It's the rough separation between one settled system and the next. It sets the cadence for colonization waves. You can talk about launch windows between stars the way we now talk about transfer windows between Earth and Mars. When you say in a neighborhood, you're no longer talking about a planetary system. You're talking about a bubble maybe 10 light years across, with multiple stars inside it. Once you think that way spatially, your sense of time has to stretch to match it. A 100-year starship is a forced lesson in long thinking. A trip that takes a century means you can't pretend big projects fit inside one career. They span 3 or 4 generations just for one leg. Colonizing a sphere 10 light years wide, with several stars inside, might realistically take 1,000 years of stepwise missions, infrastructure builds, and population growth. Mapping and lightly occupying a big chunk of a spiral arm could easily be a 100,000-year task. Those numbers sound ridiculous if you're thinking in election cycles or quarterly reports. They make sense if you line them up with stellar lifetimes and galactic rotation. Stars live billions of years. The galaxy spins once in a few 100 million. Against that, a 1,000-year colonization wave is fast. A 100,000-year mapping project is a local survey. A 100-year flight becomes a standard module on that scale, not an outlier. As soon as you accept those spatial and temporal scales, the Fermi Paradox stops being a fun puzzle and turns into something sharper. Because you just proved by doing it that a young industrial species can, with a few centuries of tech, throw a starship across interstellar space. If you can do that after a few 100 years of fossil fuels, electronics, and nuclear physics, then what about a civilization that had a head start of 1 million years, or 10 million? Physics says they could build drives, swarms, networks of colonies. Given enough time, they could touch a huge fraction of the galaxy, if they wanted to. Then you walk into your first other star system, and in this scenario, you don't see alien cities. You don't see obvious probes drifting in stable orbits. You don't hear powerful broadband beacons screaming, "We're here," across the spectrum. Maybe you find microbes, maybe you don't, but you definitely don't find anyone already running the place. That single nothing is not proof, but it's not meaningless either. It becomes one more real data point, one more local star where industrial, expansionist civilizations are not obvious. The more systems you check and find similarly quiet, the harder it is to sustain the idea that the galaxy is crowded with loud, star-spanning empires. You're pushed towards some uncomfortable possibilities, that technological civilizations are rare, that they die off quickly, that they go silent by choice, or that they use channels and physics we haven't found yet. While you're arguing about that, the risk profile of your own species is quietly changing under your feet, or under your mage boots. A species that lives only on one planet is fragile. One big asteroid, one engineered pathogen, one runaway AI, one bad war, and you can be done. Everything is in one basket, one gravity, well, one biosphere. When you put permanent populations in multiple star systems, separated by light years, you break that mode. Now, a planet killer impact in one system is a regional disaster, not extinction. A plague burns through one biosphere, not all of them. A local war can wipe out one colony, but not everyone. Risks that used to be species ending become system ending. From a math standpoint, survival becomes a network problem. As long as some fraction of your nodes stay alive and connected, the species continues. That doesn't make you invincible. You can still make galaxy-scale mistakes if you're reckless enough. But the baseline odds shift. Extinction becomes less likely by accident, more likely only by deliberate, coordinated failure across many systems. And underneath all of this, the giant timescales, the Fermi data points, the risk reduction, there's a key reframing. The arrival of that first 100-year ship isn't the end of the story. It's the opening chapter. The launch was dramatic, the century in transit was extreme, but scientifically and civilizationally, the real action starts when you're actually in the new system, taking data and building things. Every spectrum you record from an exoplanet atmosphere stops being a fuzzy hint and becomes a hard measurement. Every gravity map, every seismic trace from a lander, every magnetic survey of a new heliosphere feeds back into and rewrites models that were based on one star and one planet. You don't finish the mission when the ship parks in orbit. You start a long experiment. How does a technological civilization behave when it can't see itself as bound to one world anymore? How do biology, culture, law, and ethics change when local means a star system and long-term means 10,000 years. That experiment can, in principle, run as long as your species and your tools survive, which, with enough redundancy and care, can be as long as stars burn. Billions of years, trillions of orbits, distances and times beyond what human intuition evolved for. But the entry point to all of that is concrete and small. One ship, 100 years, one arrival. So when a starship reaches its destination after a century, what really happens is this. The galaxy stops being just a sky you look at and starts being a place you live in. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video